Good evening, ladies and gentlemen. Welcome to Reference Point. I'm your host, Dave Cokerhook, and welcome back to this second segment of conversation with Professor Silverberg, who is there at North Carolina State University. We're going to be talking more about this concept of fragments of energy. Larry, welcome back. Appreciate you sticking around for another wave of conversation here.
Nice pun.
So, in our when we ended off the last episode, we were talking about, you were giving us a bit better understanding of this concept of waves and particles and the distinction between the two, and how the concept of fragment of energy tends to tie these two concepts together in a more fundamental way. And so I wanted to pick up from where we left off there, and just take us to the next level. When you and your colleagues started to realize that some of the math might work and some of these concepts could work, how did you take it to the level of being able to validate that what you were thinking actually was working out in the physical universe?
It's a good question. So if it really did begin more conceptually, noticing, for example, that from the idea of energy flowing in space and time, that we could get conservation of energy, or that we could get wave behavior, okay? That there was a unique building block, that once you say that energy flows and you look at the building block has the same form as the gravitational energy and of other forms of energy that we see. But then we wanted to see if we could predict something with it that was kind of unique. Well, in general relativity, the first two things that were predicted by general relativity that had not been predicted before were, one of them was the precession of Mercury. And that's where, when Mercury orbits around the sun, it's an elliptical orbit, but that ellipse itself is rotating very slowly. And that's called the precession. That's called the precession of the elliptical orbit of Mercury, or the precession of Mercury. Very, very slight. And when Einstein introduced his theory of general relativity, that was one of the things that he predicted, was the first to predict that classical science could not predict. The other thing that science did not predict properly was the bending of light. Okay? So in Newtonian mechanics, the bending of light was not predicted properly. And once again, general relativity had predicted the bending of light accurately. So those were the two first problems. There's redshift, there's a number of others since then, but these were historically the first two. So Dr. Eichen and I, my co-author, we decided to apply this theory to those two problems, and that's what was recently published. We recently published a journal article in which we predicted the same precession of Mercury as general relativity, and the same bending of light as general relativity, but without using general relativity, with using these new ideas.
And you were able to demonstrate mathematically that was the case? How did you measure that?
Well, so we don't have to measure it, because we actually already have the measurements of the precession of Mercury and of the bending of light. Those measurements have already been done. So what general relativity did, and what we did, was we have a theory where on a computer we actually take the body of Mercury, and on the computer we actually calculate the trajectory of Mercury. Just like if you were throwing a basketball and you wanted to predict the trajectory of the basketball, we're doing the same thing to Mercury with this new theory, and we're finding that it precesses exactly the same amount as predicted. And
okay, so you used the simulation to identify what you believed was going to occur over X period of time, a day, a week, a month, a year, whatever. Okay. So once you then put that into place, then there was the observation of what actually occurred with Mercury during that predicted time window, and those things lined up. Is that what I'm
Yeah,
hearing you say?
that's right. Exactly. So we basically got the exact same values out to 3 or 4 decimal places.
Wow. Very
Yeah.
cool.
Yeah.
Congratulations.
And then we did the same thing with the bending of light, and also got the same results out to 3 or 4 decimal places. And then we published it.
Cool. All right. So now that we have this fundamental theory associated with fragments of energy, does this replace general relativity?
That's a really good question, because when the theory came out, there were people who are kind of worried about that, because general relativity has been with us for such a long time, and occasionally a person who might be a little irate. Okay, so I'm glad you asked that question, because I can kind of dispel a few things. So number one, we are, in some respects, because we're getting the same results as general relativity, we're actually strengthening general relativity. Okay? You could think of it that way. It just depends on your attitude a little bit, you know?
Right.
but really, we're strengthening general relativity, because completely independent of general relativity, we're getting the same results that general relativity gets. And there are those who question the validity of general relativity. Having said that, I'd also say that we only validated our theory with those 2 cases. Today, general relativity has been confirmed in many other situations besides the precession of Mercury and the bending of light. So, and we haven't done that.
So these 2 concepts, general relativity and fragments of energy, are not incongruous. I mean, it's not an either or; it's a this and type of a situation.
I think so.
Well, that's cool.
I think it's a kind of a new way of looking at it. And so what we're doing is we're predicting. So the new thing has to do with the bending of light. The bending of light is responsible for why Mercury precesses. It's of course responsible for why light, when it gets near the sun, it bends. So the bending of light is what Newtonian mechanics was failing to do. In this theory, we are bending light, and so we're kind of overcoming the same obstacle that classical mechanics had overcome, you know, but we're doing it a little bit of a different way.
Got it. Okay. I want to get into the discussion of practical utilization of the theory once there's more understanding and research and whatever. But before I get there, something that just popped into my head that I wanted to ask about is whether with the kind of work that they're doing at CERN with a Large Hadron Collider and smashing atoms and, you know, particles and waves, does this activity that they're performing, is there correlation to what you're doing, and does some of your mathematical formulae, etc., help to clarify some of the things that they're seeing that are going on when they are doing what they're doing?
I do think there is a connection, and so let me try to explain it. So in when you get to the atomic level and the subatomic level, we talk about the standard model of particle physics. Okay. And it's a very old term. You know, standard is a kind of a fun. Standard is a way that everybody is going to say, okay, you got to do it this way. It's going to be standard.
Right.
But there is something called the standard model particle physics, and there are particles and subparticles that by now are confirmed very, very well, and that everybody agree on. They're part of that standard model. But it's kind of interesting because the word is particle physics.
Right. Yeah.
The word particle physics has been around a long time. And here I'm saying that, wait a minute, maybe we shouldn't think of them as particles. We should think of them, these elements, not as particles, but really as kind of as made up of energy, not necessarily made up of particles. And actually, physicists have actually been doing that quite for a while. They usually use the word field. They call it a field. And so actually, physics has been moving in the direction of what it is that I'm describing when I say fragments of energy and things are made up of energy. Frankly, scientists have been moving in that field anyway. Now, because this is a simpler, and because I've gone behind the curtain, behind the particle and the wave to a fragment of energy, it might make it a little bit easier to look at how these subparticles kind of form into stable configurations. So
Okay.
so a fellow by the name of Mendeleev created the periodic table.
Right. Right.
When he created the periodic table, he looked at the chemical reactions and the patterns of chemical reactions, and he's famously quoted as saying it was merely linear interpolation. Probably one of the greatest achievements of all time is Mendeleev's periodic table, and he calls it just mere linear interpolation. Okay, and he was a mathematician. You know, he was not a chemist; he was a mathematician. Now, today, interestingly enough, when you use mathematical simulation on the computer and you create those electrons orbiting around the nucleus, you'll find that only certain values will they go around stable. Okay? And if you don't do the right values, then it's just going to fall apart. And so you can today on the computer recreate the periodic table, okay? And so through kind of computer thinking, you could call this, you know, through computer simulation, letting the computer help you figure things out, you can reconstruct the periodic table. What I think would be really neat is if we start to actually use computer simulation to reconstruct the structures at the subatomic level. And I think when you have simpler models, and that's what this gives you, very, very simpler models, we might actually be able to see a little bit of the rhyme and reason behind these subparticles. A number of Nobel laureates have commented on the fact that we have so many subparticles now, it's getting a little bit strange.
Yeah.
And by the way, all the different super collider folks, they all have to compete with each other. And for what? To develop a new subparticle? We already have 100 of them, you know?
Yeah, yeah. And where does that, and then that begs the question, where does that take us? And
Exactly.
so when we talk about this concept of fragment of energy as being the fundamental that from which the particles that they're identifying emanate, right? Then you can see how things just kind of like, and then it just sort of it you know it builds and it builds and it builds, and then you end up with, you know,
well, we might remember that fragment of energy came from the idea of flow in space and time. So maybe the idea of flow in space and time can be applied at these other scales and have some positive results. And so because the idea of flow is such a basic idea, more basic than conservation of energy, more basic than wave behavior, maybe we can apply this at those scales too, and it can reveal certain structures, certain stability that will help us actually make predictions. Instead of cataloging more subparticles, I think a lot of people think it's about time we start to try to find out what's behind those patterns. And that's really what Mendeleev did, you know, with molecules, right? Going from atomic up. But if we can go to atomic down and
going the other direction,
there might be some possibilities today.
Does your research or your modeling predict the ability to control the flow of a fragment of energy?
When you the research that we're doing is really more descriptive. It's describing what it is that you see.
Okay.
When you control something, you're really describing different kinds of interactions. Okay. So the word control can be used, is synonymous with maybe stability, what stays together, okay, what falls apart. But sometimes controls has to do with a path. Can you control the path of something on a higher level? Or can you control the reactions in chemistry? So once you have better descriptions of these things, you'll be able to understand the interactions better. And yes, when you understand interactions better, that's just kind of more of a basic way of saying you'll be able to control it.
Right, but we're not quite there yet.
In chemistry now, like with COVID, and the RNA, we're basically understanding the interactions much better so that we can actually, energize the RNA and get those antibodies.
Yeah,
So,
yeah. Well, you're able to, once you understand and you have the fundamentals in place, then you can manipulate, you can adapt. Okay, you put adaptive elements or activities or actions in place, which then make it possible to, for the RNA to do whatever the RNA needs to do. So, okay, so that then takes me to the question of looking at where your body of research is at this point, and where do we need to take it, and how do you make that happen? Before you start to answer that, what this reminds me of is the concept of just basic research, fundamental looking at things, at whatever we've got here in the universe, to try to come to an understanding of how all this stuff works so that we can do something with it. And I'm thinking, and I may be wrong about this, but my observation is that the support for just fundamental and basic research is not as strong as it used to be unless you're doing something for DARPA.
Okay, so there's no question that you can see this in the students who when they attend school, you can see that there's fewer students majoring in physics and biology and chemistry in the disciplinary sciences than in more of the interactive sciences, things that involve more energy and medicine and very important areas. And why does that happen? Well, we've had such great success with technology, number one, that more people are going into those areas and we've become a more technological society. But also there's a perception that all the basics has been done.
Oh, yeah.
And so, I mean, and this is just my opinion, but others might agree or may not agree. But there's no question that the number of students today that are majoring in physics or chemistry is much smaller in proportion to the other fields, the more applied fields, than it's ever been before. And so there is a bit of a de-emphasis on the basic sciences. It's part of it. I think is I actually think that there's great opportunities in the basic sciences, because where it used to be that understanding those fundamentals was for theoretical purposes, today everything we do is so interdisciplinary. The word interdisciplinary means the physics, the biology, the chemistry are all together. And if you really want to make progress, you have to understand really well, much more basically. You have to understand each of these disciplines and the boundaries between the disciplines and how they interact. And so there actually is a practical reason for understanding basic science. Now, where we are good in basic science is within the disciplines. But when they intersect, the interconnections between the disciplines we're not very good at. And so you could so the argument can be made that we're really just at the beginning of our understanding of science.
Right. Okay.
That we can understand some of these basic ideas, but how we put these basic ideas together, which means a better, more unified understanding of the basics that transcends the disciplines. This idea of universality, using the same terminology in the different fields. For example, the word energy originally was used in certain fields, but then they started using it in thermodynamics, not just in physics. They started using it in chemistry, when you eat food and you have calories. So the word energy started to permeate all different kinds of fields. And it's those universal words and the universal structures that go across the disciplines that allow us to actually figure things out today. And today, it's no more important. It's never been more important to try to go across those boundaries in the different disciplines and create common languages. Of course, it's not just in science. Common language, the barrier of language and the barrier of different philosophies is really where we want to go today in the world. You know, so much of the conflict that we have today, not just in the sciences, but in economic systems and political systems, is because we need to get beyond the disciplinary expertise and start to really value the connections.
Are you seeing this begin to happen
Well,
within the framework of science?
Yes, I think I am, because you've actually seen in physics, the people doing basic physics, the people who are doing some of the best basic physics are in all different kinds of communities now.
With all the work that you've done thus far, Larry, in terms of the research and the additional mathematics that you've done, et cetera, have you reached a point where you are able to predict in some, at some level, what you think the practical utilization of fragments of energy might be?
I think with sometimes you have to stay within what you're doing and understand kind of the value of what it is that you're doing. So I think the value of the basic research is in the clarity that it brings at the scale of what it is that we're doing, in the confines of what we're doing. So for example, being able to show how more complex behaviors can be understood easier, okay, is kind of where we're at. That's the kind of stuff. So the papers that will be coming out in the next, several years will be about all different kinds of problems that we can solve using this idea, so that people will grow comfortable with the idea. They'll see the strength of the idea. For example, in the last show, I showed the flow of energy.
Right.
Okay. Well, that was a visual, just showing the flow. Well, I can imagine that just by looking at flow of energy in all different complex systems, that's a way to understand what's going on. So that in itself is even a visual, okay, that would be used in the past, that would help people understand kind of what it is that they're looking at. So we have some plans of basically doing basic things, not particularly applied, but really showing how you can see things more easily with these ideas. Okay,
very cool. So we have about 4 minutes left in the show. I wanted to touch on one topic. When you and I first reached each other and started talking, you told me something I thought was real interesting, that you've gotten some feedback from certain people, and some folks were like, oh, a little frustrated, and said, we've known this in mathematics, blah blah, for a long time. But you actually received from positive feedback from a section of the population that you weren't expecting. I guess it had to do with folks that are more on the, the non-physical or the metaphysical or religious side of perspective, because as we come to understand the physical universe and how does that hit belief systems and things like that, you actually receive some positive input. Is that correct?
Yeah, it was kind of interesting. I've gotten wonderful feedback from just about all the different religions. So Jews, Christians, Hindus, who can relate to the idea that everything is made up of energy and elements of energy. I mean, if you think about it, in the Old Testament, let there be light. And the idea that there's this, and energy is a less tangible idea than a particle. And so in religious teachings, this idea of us all being connected, interconnectivity and energy, actually is pretty consistent with what people have believed in all different kinds of faiths. So I do think that it seems to have resonated with these groups of people. Actually, it's kind of interesting. The ancient Greek Heraclitus, okay, he was one of so during the times of ancient Greece, there among the communities credited with the elements of nature being earth, water, air, fire, and ether. But Heraclitus had a different idea. And he said that everything flows, and there's images that have been created with Heraclitus in a river of everything flowing. And I think it's kind of funny, because here we are in 2020 talking about how energy flowing, from that you can get these different ideas.
Yeah, so we're going back to fundamental knowledge, basic knowledge that was
well, I don't think it's a coincidence, Dave. I think it's because of it's very instinctive.
Yeah.
And I think what's happened is the mathematics has caught up. We also have to remember that the first mathematics was with particles, and then the mathematics was with waves. And
Yeah,
it's naturally took a while to bring those back together a little bit. And
that's very
so,
cool.
and so I do think we're seeing the interconnections being strengthened with some universal ideas. And so I think that's a good thing.
I think it is a good thing. Well, Larry, we've got just about a minute left in our show, and I'm wondering if you have any last thoughts that you wanted to convey to the viewers.
Well, I think the last maybe point I might make is that science has really only begun. We have science in silos, but we haven't really brought the different disciplines together. The interconnectivity is kind of what's missing, and hopefully a little bit in a very small way, what myself and Dr. Eischen and some of the others are working on trying to kind of understand the interconnections a little bit more. I think it will go a long way, and I think we really are just beginning. So for those who are interested in the basic sciences, I think it's one of the great areas also to work in.
Fantastic. Larry, thank you so much. Ladies and gentlemen, I really appreciate your being here at Reference Point. There will be information in the show about how to read the paper, how to reach out if you want. You can reach Professor Silverberg through me, and we'll make sure that you have get answers to any of the questions that you might have. So Larry, again, thank you so much for being with me for these 2 episodes of Reference Point. Fascinating information. And I really look forward to seeing your next paper.
Okay, thanks. Appreciate it.
Bye-bye, everyone.